Let's look at reaction energy diagrams. So we should pay attention to the energy that our reactions either generate or use. And one of the ways to look at this is to draw a reaction energy diagram, or these are also called a reaction coordinate diagram or reaction progress diagram, something like that, or there's lots of names. So down here, we would choose to say this is the reaction coordinate. Another way to think of this is a reaction progress. So we'll start here on the left with reactants, and we'll progress through some energy transition states or on the way to our products, and then we will end at the products. And since this is an energy diagram, our y-axis, or this vertical axis, is energy. Like so. So we'll start off with some reactants. And as an example, what if we had some hydrochloric acid and some hydroxide ions? So these are going to react with each other. And initially, it's going to take energy for this reaction to start. That is because we have to break the hydrogen-chlorine bond. Or if it's in water, we'd have to break the H plus to water bond. Either way, we're going to have to put in some energy to get this reaction going. And then as the reaction progresses, this will come down to our products, which is the chloride ion and water. So right at the top, we have our transition state. And there's an energy of activation. So the energy that it takes to get up to the top of this transition state. And some people will label this delta G naught double dagger. So delta G under standard conditions, and then double dagger is indicating that it's going up to the transition state. And then we could have the delta G of the reaction. So that's the energy difference between the reactants and the products. This is an example of an exergonic reaction. Because delta G was negative. This is also known as a spontaneous reaction. That is, as long as we have the energy of activation, then we will reach the products. If we don't have the energy of activation, then the reaction will still not happen, even if the reaction is spontaneous. And perhaps it's a poorly chosen word. So I'm going to draw another reaction coordinate diagram. This time I'm going to start with the chloride and the water, and I'm going to end with HCl and OH. So you'll notice that my reactants are lower energy than my products. And in this case, the energy of activation, or the activation barrier, is much larger because I have to go all the way from where my products are back up that hill to get back to the transition state. And you'll notice that my delta G of reaction is now a positive number because I had to go up from where I started. So this is an example of an endergonic. And that is, we have a positive delta G. And this is not spontaneous. We can connect both of these, or all of this, to our equilibrium constant, because equilibrium is really a thermodynamic related process. And so we can do that by looking at our delta G reaction. So if we start off remembering that it's products minus our reactants, and that is going to equal delta G for the reaction. But further, that's also equal to negative RT, so the R is the gas constant, but make sure you're using the right units on R, the 8.314, and that's the one in joules and mole Kelvin. And then we have the natural log and the equilibrium constant. So you can see, hopefully, that, well, R is a positive number and temperature is a positive number because you should be using Kelvin in this. You need to use absolute temperature. And so both of these being a positive number, that means if delta G is negative, that K would have to be larger than 1. And that is, again, another way of saying we have a product-favored reaction. If K was, or if delta G was positive, then that would force the Ln of K term to be negative. And that can only happen if K is less than 1 or small, which means that we have a reactant-favored condition. So that's a little bit about reaction energy diagrams and just what to look for. This can help us see which way a reaction would go and think about how we get to the transition state and what's happening along the way for our reactions. So thank you for joining me, and we'll see you in the next video.